Hello everyone. So now we will discuss in part 2 that resonance effect, and then after we will move on for hyperconjugation effect, plus H effect, minus H effect, and then after we will discuss SIR effect, steric inhibition of resonance, and at last we will conclude aromaticity, aromatic compound, non-aromatic compound, anti-aromatic compound, their stability and heat of combustion also we will complete in this segment. So let's start that last segment as we discuss that resonance effect and resonance difference. So there are two types of resonance. One is plus R effect and another one is minus R effect. So plus R effect is shown by those compound which is containing lone pair. So this electron, since conjugated system is there, double single double is connected with this. So high electron density to low electron density, electron will move. Like here, suppose for example, carbon double bond carbon, single bond carbon double bond carbon, and with this is connected your NH2. So this NH2 and here this pi bond means here that one p orbital is there, right? This one removing here this. So overall you can see here this pi bond also I can make like this, right? So overall you can see that here that one pi bond, here one pi bond, here also overlapping will happen, and this lone pair since adjacent is p orbital, so this electron also will be lone pair will be delocalized lone pair, means in pure p orbital, and electron will move from high electron density to low electron density as we discuss in classes also in detail. So that those attached atom or group, if it is giving electron to the conjugated system, then it is called that plus R effect. So all that in gist you can remember, all lone pair containing compounds are plus R effect. This all those plus R effect. In that you can see this all those are a strongly activating group. Activating means they are giving electron to the conjugated system. Here this one is also giving, but since you can see it can give also to the conjugated system, but this lone pair single bond double bond means this electron can move this side also, so that this lone pair having partial delocalization towards the conjugated system, means they are called moderately activating groups. Here you know that pi bond, so pi bond also can delocalize. So depending upon that conjugated system, if in conjugated system if any electronegative atom is there, so this pi bond will get directed towards the ring or towards the conjugated system, means such type of groups are adjustive group. They can behave as a plus R also, minus R also. If conjugated system having nature of electron withdrawing, so they will withdraw the electron from this double bond. Similarly, this benzene also is adjustive group, can behave like plus R, can behave like minus R. If it is connected with conjugated system, and conjugated system nature is that electron withdrawing group, so it will withdraw electron from here, means it is donating the electron, hence it is also plus R effect. Now moving further, you can see halogens, fluorine, chlorine, bromine, iodine, so they also contain lone pair. So since they contain lone pair, so they can behave as a plus R effect, but overall their minus I is dominating due to its electronegative nature. So overall it is electron withdrawing group rather donating, even though it is plus R effect, but it is overall electron withdrawing group. Next, moving minus R effect. So minus R means those attached atom or group which is giving electrons, which is pulling electrons, taking electron away from the conjugated system. So such type of attached atom or groups are minus R effect. So like here you can see plus charge, so means it will withdraw the electron from the conjugated system. Here BH2, so BH2 having that vacant p orbital, so it will also withdraw the electron from the conjugated system to make their octet complete. Similarly, here you can see this in that carbon oxygen bond. So this pi bond is getting delocalized towards oxygen. So this carbon will withdraw the electron from the conjugated system. Will withdraw the electron from conjugated system. Clear? Will withdraw the electron from the conjugated system. So this all those are electron withdrawing group. This carboxylic acid and its all derivatives are electron withdrawing. So let's suppose, for example, this benzene, with benzene, if electron donating group is attached, so they will give electron at ortho and para only. In class we discuss. So if it is giving electron only at ortho and para, means electron density in this benzene now increasing due to this electron donating group, due to plus R effect. So that if electrophile is coming, so electrophile rate will be higher at ortho and para, because overall here electron density is higher. Means electron donating groups are ortho para directing groups, and rate of electrophile will be here more. Means welcoming nature of electrophile will be here more, because electrophile is electron deficient and this ring is more electron efficient due to this electron donating group. Electron density is more at ortho and para. Then after benzene, whereas this benzene ring, as it is connected to electron withdrawing group, so electron withdrawing group will withdraw electron from ortho and para. So as they are withdrawing the electron from ortho and para, electron density at least at meta will be as like normal benzene. So if electron density at meta is more, so at least electrophile will come at meta, means they are called deactivating group and they are meta directing groups, since they are withdrawing the electron, and at meta somewhat electron density is normal, so electrophile will come here. So rate of electrophile welcoming nature will be first at this, then after this, and at last here. One very important point you try to understand and remember, that for this halogen, if halogen is connected, so overall halogen will withdraw the electron, but since it having lone pair, so it will give electron at ortho and para through resonance. But resonance plus R effect is not that dominating, but while making product, pi bond is weaker, so we will form product through plus R, but rate of formation of product will be slow, because overall its minus I is greater than plus R. So that only here you can remember for halogen, always remember this, for halogen, while rate we will determine minus R is greater than plus R, but while making product, plus R is the prominent over minus I. Orientation of electrophile means where to add electrophile. So while adding electrophile in conjugated system, in benzene system, always we will decide by plus R, or by rate we will decide by overall electron density. So minus I, actually minus I is greater, but for product only we will consider through pi electron, means R is a deciding factor. Clear? So for rate, minus I is greater than plus R, and for orientation or product formation, plus R is greater than minus I. Next, after resonance effect, now we will understand like resonance, hyperconjugation. Like resonance is the happening in that conjugation, like double single negative charge, double single positive charge, double single free radical. Similarly, hyperconjugation, how it will happen, like suppose this is toluene. So in this, you know that this benzene in that orbital diagram, so this is overlapping with each other, this one is overlapping with each other in a realistic manner. Now here you can see this carbon, so this carbon is sp3, so these two are above and below, and this is in plane with this benzene system. So here you can see this is the sigma bond carbon hydrogen, so here 2 electron, and in p orbital here 1 electron is there. So some electron density will move from sigma to this pure p orbital. So that delocalization of, before that in resonance what happening, pi electron or delocalized lone pair was moving in conjugated system. But now here what happening? Sigma electron relatively stronger, so its delocalization or polarization will be not that effective, but at least somewhat electrons are moving. That sigma electron is moving to pure p orbital. So that delocalization of sigma into pure p orbitals is called hyperconjugation. An electron is moving from high electron density, since here it is 2 electron, here it is having only 1 electron, here it having only 1 electron, so electron is moving in this manner. So this is called hyperconjugation. This is called hyperconjugation. So what is the condition? That first carbon must be sp3, it should have alpha hydrogen, and adjacent carbon should have parallel p orbital. Then electron will move from high to low. Since it is not like resonance, that resonance in that pi electron was moving or delocalized lone pair was moving, so here electron density will be not relatively that much moving, delocalization, transfer of electron, but yes, somewhat happening, and this effect is only, this phenomena is only called hyperconjugation. Means either this hydrogen or this hydrogen or this hydrogen, this bond order is not 1, because these electrons are moving high to low, so overall their bond order carbon hydrogen is greater than 0 but less than 1. And overall, since these electrons are moving high to low, so here partial positive charge and overall partial negative charge where at ortho and para. So plus H effect also in benzene system, ortho para derivatives. In class we discuss its structure also. So this effect was given by two scientists, Nathan and Baker effect. We studied in class that how it, in detail, that how it happened. So here that hyperconjugation involves sigma bond in p orbitals overlapping. This is also called Nathan-Baker effect, and resonance effect is more than hyperconjugation. Hyperconjugation is more than inductive. Clear? And this is also permanent effect. Why permanent effect? Because once electron is transferred here, now from here electron will move to ortho and para equally. So this is permanent effect. Electron, this is distance independent. Next, moving further, now we will discuss there are two types of effect, H effect, plus H effect and minus H effect. So plus H effect is what? If attached this sp3 carbon, electron, sigma electron is moving to conjugated system, means it is giving electron to conjugated system or that benzene system, then it is called plus H effect. So here you can see p orbital, means here it having only one electron in p orbital, whereas sigma having two electrons, so overall electron moving. So carbon must be sp3, it must have alpha hydrogen, and here must be that parallel adjacent should have that pi bond, means p orbital. Then hyperconjugation will happen. So here hyperconjugation happening, here also hyperconjugation. How? Like here, let's suppose free radical is there. So free radical means here free radical means one electron, but here it having two electron. So yes, electron will move. Here carbanion. So carbanion means here it is negative charge. Negative charge means here that already two electron is there, right? And here also two electrons. So electron will not move from that two electron means electron cannot move. Almost electron density is equal. Somewhat here it is less only due to sigma bond. So electron cannot move. Even that here adjacent it having lone pair. If lone pair, even it will degrade its hybridization. Let's suppose little bit like here that CH2. So here hydrogen is there, here hydrogen is there, and here this is negative charge, and here carbon, hydrogen is there. So let's suppose this is the sigma electron. Even it will degrade its hybridization from sp3 to sp2, and it will keep it in pure orbital. So here two electron and this sigma electrons are strong. So it's these two electrons are relatively less polarization. But here also two electron, here also two electrons. So polarization cannot happen. Means hyperconjugation cannot happen in carbanion system. only for carbocation and carbon free radical possible. Next, here you can see, here it having positive charge, and along with that, so here positive charge means vacant orbital. So clear? So here you can see it having vacant, here that p orbital, and here that sigma electron, so can move. So total how many? 9 alpha hydrogen, so hyperconjugation can happen. Similarly here you can see that here this is the sp3 carbon, but is not having alpha hydrogen, so no hyperconjugation. Now we will study that hyperconjugation when it is happening, so like resonating structure, hyperconjugation structure. So let's suppose, for example, here you can see that this alpha hydrogen that is breaking the bond completely. Hypothetically we are thinking this is hyperconjugation structure, so they are hypothetical structures. So here this is that this total 2 electron, so here that you can consider like that lone pair, single bond, double bond. So overall double bond came here and negative charge is here, and this is the positive charge. So this is hypothetical structure where what happened, that hydrogen bond completely gave their sigma electron to adjacent p orbital. So similarly this hydrogen is giving, similarly this hydrogen is giving. So you can see this 3 hyperconjugation structures, in that carbon hydrogen bond is involved completely, whereas here it is not involved. Here just that hyperconjugation structure without involving CH bond. So total with respect to this 4 hyperconjugation structure we can draw. So here you can see carbon hydrogen bond greater than 0, less than 1, all having +1, and here it is partial negative, and electron density moving from high to low like this. Clear? So this is hyperconjugation hybrid actual structure. Now coming to ethyl carbocation. So in ethyl carbocation also you can see that here this sigma electron moving to vacant p orbital, high to low, like that all those hydrogen can move. So in ethyl carbocation what happening, sigma filled electron is moving to p vacant. So this is one hyperconjugation structure for ethyl carbocation. Another what is possible, if whenever suppose vacant p orbital is not there, like here that this is the CH3 means sp3 carbon having alpha hydrogen, and here already having pi bond. So if it is having pi bond, so this is its pi star, this is what it's pi star. So for time being electrons are moving from sigma to pi star means, and after that this bond will break means again electron will go from pi star to pi. So for time being as electrons is moving to pi star, so sigma filled moving to pi star vacant. So there are this only 2 possibility, that sigma carbon, that alpha carbon hydrogen moving to either vacant p orbital. This is only possible in carbocation and carbon free radical. And another is possibility that CH3 along with that conjugated system. So in that pi bond is already there. So sigma electron will move to pi star. So when that sigma electrons is moving to pi star, then this is another possibility. Sigma filled is moving to pi star vacant. Total number of hyperconjugative hyperconjugation structure, hyperconjugative structure. So one that you saw that which is not involving CH bond, and remaining 3 involving CH bond, that in propene. So total number of hyperconjugation structure will be what? 1 plus total number of alpha hydrogen. So if they are asking total number of hyperconjugative structures, so calculate the total number of alpha hydrogen plus 1. Stability of alkene is directly proportional to number of alpha hydrogen. Next, moving further, like here you can see this is one alkene, so it having how many alpha hydrogen? 2 here, 2 here, 2 here, 2 here. So more the number of alpha hydrogen, more will be stability. So here how many? It's having hyperconjugative structure. If asking only involving CH bond, so total here 8. Here how many alpha? here 1, here 3, and here 2. So total 1, 3, 4, and 2. Total 6 hyperconjugative structure which involving CH bond. Now you remembered I told IT sector, like for inductive effect, tritium having more plus plus I effect. Here since carbon hydrogen, that carbon tritium. So here what it will be, opposite of that. I'm sorry, this one we need to correct. So here it will be that more plus H effect will be first CH3, then deuterium, then tritium. Why? Because carbon hydrogen bond, that electron density is weak, bond length is more, so that can more polarize, so hyperconjugation is more. Then after deuterium, then after tritium. Minus H effect is not that much is there in our syllabus in advance. So minus H effect or reverse hyperconjugation only shown by this one molecule, that is carbon double bond carbon along with this trichloro system. So in that again, like there carbon hydrogen bond involved, so here also this is sp3 carbon, and in that this chlorine bond is involved, then after this chlorine bond, and then after this chlorine bond. So overall this lone pair is moving from here to here. So like this means, like suppose for example here that CH3 CH2, so CH2 positive, yes, here, yes, so here that double bond was missing, so double bond. So now bond as it is breaking like this, so here positive charge came, so this chlorine bond is involved, right? Similarly we can break this one also or this one also. So overall here it is 3 partial positive charge, 1 2 3, and here it having partial negative, partial negative, partial negative. So overall 3 partial positive, 3 partial negative. So this is the hyperconjugative structure for minus H effect. Now moving further, if charge containing atom is not same, then we will not determine that stability through resonance hyperconjugation. Then only we will decide its stability by electronegativity, hybridization, angular strain, and so on and so forth. If charge contain, once again I am telling here, charge containing atom, charge containing atom, charge containing atom, this all those are same, means this is also sp2 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 sp2. Is that clear? So if charge containing atom is same, then stability is determined by then resonance hyperconjugation. If it is not same, then we will decide by electronegativity, hybridization, angular strain. Some example we will discuss. Like here you can see that here it having, so first factor which one, resonance. If resonance is not happening, then hyperconjugation. If it is not happening, then inductive. So here how many that hyperconjugation happening? No, not happening. Here it is positive charge, how many alpha hydrogen? 3. Here how many alpha hydrogen? 6. Here how many? 9. So more the hyperconjugation, more will be stability. Since resonance not happening, so here hyperconjugation more, so it is more stable than this, and here this is just reference atom. Next after similarly here also hyperconjugation more, so it is more stable. But here you know carbon ion hyperconjugation will not happen. So here this CH3 is plus I donating group, here donating group, here donating group. So here electron density as increases, so stability decreases. More the charge containing ions, more will be, means less will be stable. So here this one is the more stable. Next, moving further, like here you can see in this conjugated system, positive single double. So here due to conjugation resonance happening, not resonance effect. So here also, so here due to resonance it is more stable, here also this is more stable, here also due to resonance high electron density to low electron density. We discuss orbital diagram. So this one is moving, so overall this is more stable, all one is more stable than 2. Next, moving further, here you can see that carbocation and here fluorine is there. So electron density of one fluorine delocalized lone pair moving from high to low. Similarly, this one also back bonding doing moving high to low. This one also moving high to low. So this is 2p overlapping, whereas chlorine back bonding is 3p. So overall 2p is prominent. So that is more stable. One is more stable than 2. Similarly, here you can see this is carbanion. So carbanion already having 2 electron, here also 2 electrons. So electron cannot move high to low. So it having only that minus I effect. So through minus I, it is withdrawing electron, right? Whereas chlorine, in that chlorine, it can withdraw through minus I, but chlorine is since third period element, so it having vacant d orbital. So electrons of carbanion can move from high to low. So due to its charge density decreases, so overall through minus R, chlorine having adjustive group, it can behave like a plus R also, it can behave like a minus R also if it is required. So here it is through minus R, it is more stable, so 2 is greater than 1. Next, moving further, like here you can see free radical. So in free radical, that fluorine having 2 electron and here carbon radical having 1 electron. So it can move high to low. Electrons are getting polarized. But in chlorine, what will happen? One chlorine is giving another chlorine can behave like Lewis base, means it having vacant orbital. So here electrons are going. So overall electrons are moving like extended conjugation, means electrons travels more distance. Here high to low, and then after from here high to low. So this effect is called push-pull effect of chlorine. Hence this one is more stable in free radical. Now stability of carbocation is very important. This one you can see, this one is that dancing resonance or sigma resonance. Sigma resonance is more stable. Then after quasi aromatic, then after 3 degree pH, this is benzene, so phenyl, so 3 pH3C positive, then pH2, then pH CHR in class I discussed, then 3 degree, then after pH CH2, then after this allylic system, then after 2 degree, then after 1 degree and primary 1 degree, then after double bond, and at last triple bond. Clear? So this order also you remember for stability of carbocation. Next, moving to heat of combustion. So heat of combustion is what? That enthalpy change when 1 mole of any substance is completely combust in excess of oxygen, that is whatever amount of energy is released, is called its heat of combustion. So you can see here that for starting, that for any substance, that little bit ignition temperature we need to provide, and then after it will burn completely. So heat of combustion, that after burning, after combustion, that whatever amount of energy is releases, that is, let's suppose Y, and we gave X, so total heat of combustion per mole is Y minus X. So heat of combustion, always apply this rule in sequence. Heat of combustion directly proportional to number of carbon. More the number of carbon, more will be its heat of combustion, correct? If number of carbon atom is same, then inversely proportional to stability or directly proportional to strain, means those compound which is less stable will be more reactive, will having more strain, they having more heat of combustion. What is meaning? Means suppose for example, this compound is less stable. So if it is less stable, means highly reactive. If it is highly reactive, means its ignition temperature less I required. X value is less. So overall Y minus X will be greater. So heat of combustion also will be greater. So coming through example, like here you can see first example. Here how many carbon? 7 carbon. Here 6 and 6. So 7 carbon heat of combustion will be more. Now here we will apply rule 2. So in this 2 carbon, which one is more stable? This is double, single, single, double. Whereas here double, single, double. So here due to conjugation, this is more stable. So if it is more stable, so its heat of combustion will be less. Why? Because its X value, ignition temperature relatively will be more than this. So 1, then after 2, then after 3. 3 heat of combustion will be less. Now coming here, This is 3 carbon, then after 4 carbon, then after 5 carbon, then after 6 carbon. So more carbon, as it is expected, heat of combustion should be more. But this all those structure, in that only one is planar, remaining all are sp3 carbon, so they are non-planar, so they having different angular strain, so we don't know their stability. So first in class we discuss in detail. So first we will make it strain free. So to make it strain free, let's suppose this one by complete combustion it is giving energy x, this one is giving y, this one is giving z, and this is giving w. So if this carbon, that here how many carbon? 3 carbon. So if that whatever amount of energy it releases by complete combustion divided by 3 if I am doing, means now for 1 carbon heat of combustion. So for 1 carbon heat of combustion is now strain free, shape free, orientation free. Means x by 3 experimentally we saw that this value is greater than y by 4, and y by 4 is greater than z by 5 and w by 6. Means its heat of combustion is more. So if its heat of combustion is more, so we know that heat of combustion is inversely proportional to stability. So if its heat of combustion is more per carbon, then its stability is less. So bare angular strain not properly discussed that stability of this cyclo compounds. Who discussed that stability of all those cyclo compounds? Heat of combustion value. So more the heat of combustion, its stability will be less. So this is the less stable, and here heat of combustion is relatively less, so it is more stable. That's why 6-member cyclic compounds is more stable than 5, 5 is more stable than 4, 4 is more stable than 3. Clear? Next, moving further, this one. If suppose all those having 6 carbon, then more the number of carbon, more will be that. So here you can see that here it having 6 carbon, here also 6 carbon, here also 6 carbon, here also 6 carbon. So which rule we will apply? Rule 2. So number of carbon atom is same, then inversely proportional to stability. So which one is 3-membered is less stable, then after 4, so its heat of combustion will be less stable, means heat of combustion will be more. So 1, 2, 3, 4. Next, sigma or dancing resonance. So in CPM, cyclopropane methyl cation, in cyclopropane methyl cation, usually high stable due to sigma resonance. This is only one compound, sigma. Due to sigma resonance it is more stable. It is not like hyperconjugation. Only in this, due to that 3-membered cyclic ring, it is unstable, so electrons are moving from high to low. So you can see as this electron is moving, so one resonating structure, this is another, this is its hybrid. So in 3-membered cyclic, that cyclopropane methyl cation, when sigma electron is moving to vacant p orbital, this is called dancing resonance or sigma resonance. Clear? Now coming to SIR effect, steric inhibition of resonance. You know that resonance only will happen to in planar system, and resonance or even hyperconjugation will happen in only planar system, and it will happen when that yes, in planar system, and second that when electrons will get delocalized through sigma or delocalized lone pair in conjugated system. Once again, resonance and hyperconjugation will happen in planar system, and second that only resonance and hyperconjugation happens in pure orbital. In hybridized orbital, resonance and inductive effect cannot take place. So here you can see that at ortho in benzene system or conjugated system, at ortho if bulky group is there, and here that attached atom also having bulky group, so due to that bulky group it will have ring repulsion, and due to that repulsion this sigma bond will rotate. As it will rotate, so this lone pair cannot get delocalized with this conjugated system. That is only called SIR effect. Clear? So when this is getting rotated, so it will become perpendicular, means this lone pair will become perpendicular, means it cannot delocalize with this conjugated system, means now the system will behave as minus I only, because nitrogen is electronegative, so it can withdraw electron from carbon, means it can only behave as a minus I, it cannot behave as a plus R. So only at ortho, like here that ortho substituted if bulky group is there, and along with that here also if bulky group is there, then only Sir effect will happen. Like here if bulky group is there and this is aniline, hydrogen there, then hydrogen will not feel that repulsion, then there no Sir effect, means this lone pair can delocalize, electron can move from high to low. Understood? So here these are the condition. Only ortho substituted large group can show Sir effect. Like here you can see a small atom cannot show Sir effect, like fluorine, chlorine, bromine, if it is attached here. So no problem, they can do plus R. If a small atoms are there like NH2, OH, OR, no problem, they can do. Even ortho substituted groups are there, they can do resonance. Linear groups are there, like here linear group, then also no problem, no repulsion will happen. If any non-planar compounds are there, non-planar means already it is perpendicular, like here sulfur double bond oxygen, sulfur double bond oxygen. So here no lone pair is there, it was already not doing resonance, it was doing minus R effect. So here that no problem at all. Here also no Sir effect applicable, but only for those which compounds having like attached atom or groups having here bulky group, and at ortho if bulky group is there, then only it will rotate and it cannot do plus R. Clear? So here as I discussed in sulfur, that since it is already perpendicular to the plane, so here it is behaving like an electron withdrawing, so here no problem at all. Next, which of the following can show Sir effect? So you can see that Sir effect is applicable on this nitro group or this bulky group, at least one bulky group, or here this all bulky groups. Yes, this all those will rotate, all those will rotate, all those will rotate. Sir, this one also, this one showing minus R effect, so this will also rotate. Even it will rotate also, no problem at all. Even it will be perpendicular. So due to that perpendicular, what will happen? So here don't get confused that here already it is perpendicular and these orbitals are also perpendicular. So here by default it will happen. Here no steric hindrance. This is already perpendicular. So here minus R effect can happen. But remaining all those will rotate. So as it will become perpendicular, then it will not show resonance with conjugated system. Now here we can see some examples. Like here you can see cyanide, CN, it is linear, and here that also substituted, no problem at all. It can show minus R or minus I also showing. Here you can see NH2, NH, that nitrogen, not H, nitrogen, methyl and methyl. So here it is showing plus R, but if this group is associated with ortho, then it will rotate. Now it cannot do plus R, it can do only minus I. Coming to Brett's rule. So Brett's rule is what telling that planarity never can be achieved at bridgehead center of the bicyclo compounds containing 8 or less than 8 carbon. Means if 8 or less than 8 carbon, if it is there you cannot draw planarity, means carbocation, carbon free radical, double bond, means at this bridgehead we cannot draw sp2 entities. That's why in tautomerism also, here tautomerism cannot possible, means this all those entities do not exist, they are not real. Whereas you know that this carbanion is sp3 entities, yes it can exist. Yes, here boron, it is sp2 entities, so sp2 cannot exist? Yes or no? Because it having vacant p orbital also. So it is sp2. No, it cannot exist. Yes, nitrogen can exist, sp3. Clear? So planarity means sp2 entities cannot exist at bridgehead center. Who told? Brits. And for that, why it will not exist? Through that all those that drawing we understood. So here just you remembered that here planarity, that all those that carbocation, carbon free radical and alkene system do not exist at bridgehead position. Bridgehead position. Moving further, like here you can see charge containing atoms are different. Charge containing atoms are different. So will not decide here stability by resonance, hyperconjugation or inductive. So here we will decide by hybridization sp3, sp2, sp. So since this is sp, so percentage of s character is here more. So it will withdraw the electron. So here positive charge will increase. So this is less stable. So which one is more stable? 1, then 2, then 3. Similarly for free radical. Whereas in carbanion, here this is more withdrawing because percentage of S character is 50%. So this is relatively more stable than this. So 3, 2, 1. Next, moving further, resonance and hyperconjugation do not participate in hybridized orbital. Like here you can see carbocation is generated at sp2. So even though here hyperconjugation is happening, hyperconjugation is ortho and para. So this is ortho and this is para, but this carbocation is present in hybridized orbital. So hyperconjugation cannot stabilize this carbocation. So this carbocation is less stable. Clear? Next, after that, here you can see resonance also cannot help. So resonance and hyperconjugation never occurs in hybridized orbitals. So here we will see only through sigma resonance. Sigma resonance can happen. Sigma bond, you know that it is in hybridized orbital. So this CH3 is giving electron. OCH3 having minus I effect. NO2 also having minus I. In OCH3 and NO2, you know that NO2 having more a strong minus I. So this is relatively less stable, relatively unstable than this one. So which one is more stable? At least this one is getting electron. So 1, then after 2, these two are withdrawing, minus I. In that this one is just strongly withdrawing. So then after 3 and then after 4. Next, stability of this carbocation. Some examples we will discuss. So here you can see positive. So electron will move with this oxygen having 2 lone pair. In that one will be delocalized. So electrons are moving high to low. Electrons are moving high to low. So here since back bonding happening 2p, 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 2p. Whereas here 2p, 2p, here 3p, 2p. Here 3p, 2p, 3p, 3p, 2p. So this one is more effective back bonding than this, than this. So 1, 2, 3. Now carbanion is there. So carbanion means now electron cannot move from here to here, both having 2 electron. So here it having minus I effect, here also it having minus I effect. Here minus I, but this sulfur, you know that third period element, so it having vacant d orbital. So back bonding can happen from 2p to 3p. Here also adjustive group. So vacant d orbital, vacant d orbital. So electron can move, electron 3d. So 3d vacant orbital. So electron can move from here to here, high to low, high to low. So third is more stable than 2, then 1. Now coming here carbocation. So here due to hyperconjugation to hydrogen, it is getting stabilized. But here through conjugation, positive single double. So you know that resonance is more prominent than hyperconjugation. Here that resonance is happening, that positive single double. But overall always remember that stability order is determined by first that by sigma resonance, after that quasi, aromatic, after that by aromaticity, then after resonance, then after hyperconjugation, then after inductive. I repeat that stability first we will determine by dancing resonance or sigma resonance priority order. After that we will discuss by that by this. So first we will discuss by that dancing or sigma resonance. After that second we will decide by that this one quasi aromatic. What is quasi aromatic we will cover in this segment only. After that aromaticity, after that resonance, hyperconjugation and inductive. So here you can see that it is anti-aromatic 4 pi electron. So it is unstable even though conjugation is happening. So here it is, which one is more stable? Second, then after first, and then after at last third. So third is relatively less. Now coming here, so here you can see positive single double. So here the conjugation there. Here positive single single, positive single double. So here you can see more resonating structure as compared to here. You can count also. So overall here resonating structure is 7. So 2 is more stable than 1. Now last segment we will discuss aromaticity. In that aromatic compound 3 definitions are there, that those compound which is obtained on fractional distillation of coal tar, it having one particular aroma, that's why it is called aromatic compound. Compounds having induced dimagnetic ring, or that cyclic compound is more stable than its analogous open compound. Like here you can see that this carbon having how many carbon? 6 carbon. Here also 6 carbon. Here double single double single double means 3 pi bond is there. Here also 3 pi bond means both are analogous. In that cyclic compound is more stable than open. What are the conditions or characteristics for aromatic compound? Compound must be cyclic. Compound must be planar. Compound must be cyclic conjugated. Like here we saw double single double single double single double single. So this is conjugated. And fourth rule is that Huckel rule, means it should have 4n plus 2 pi electron. N value could be 0, 1, 2, and it is valid for monocyclic compound. If more than one cyclic compound is coming, then this Huckel rule is not valid. There I will tell how to find out aromaticity. Next, anti-aromatic compound. So anti-aromatic compounds are all cyclic compound which is less stable than their open analogous compound, open chain. Like here you can see 4 carbon, here also 4 carbon, 2 double bond, 2 double bond. So this cyclic compound, more than that, open its analogous compound is stable. Why? Because it can do flipping and it can form this. So overall angular strain 120 degree angle, and since this carbon is sp2, so sp2 means also it is trigonal planar. So overall angle is must be 120. So 120 minus 120, angular strain is 0. But here angular strain you can see this is 90 degree and this carbon is sp2. So expected angle is 120 but actual angle is 90. So overall angular strain is 30 degree. So this is relatively less stable and this is relatively more stable. This is also cyclic compound. It is also planar and it is cyclic conjugated, and Huckel rule will be 4n pi electron, n value 1, 2, 3 means 4 multiples pi electron will be there. Non-aromatic means those compounds which is neither aromatic nor anti-aromatic. Those compounds are non-aromatic. Stability, most stable is aromatic, then after non-aromatic, after that anti-aromatic. Cyclic compound containing more than 7 carbon, if it is anti-aromatic, then it will become non-planar and it will become non-aromatic rather than being anti-aromatic, because non-aromatics are more stable than anti-aromatic. Anti-aromatic compound do not exist at room temperature because they are unstable, so they get dimerized. So here you can see they are getting dimerized. Same we discuss in Urj reaction also. Next, anti-aromatic compounds are not stabilized by resonance. Why? Because in resonance that distance must be same, like benzene, in that all carbon carbon bond length is same because bond order was same. Here bond length is different. Here this is y and this is z, so you can see that y and x is not same, so that delocalization cannot happen. So there is no meaning of here conjugation, means anti-aromatic compounds are not stabilized by resonance and all. Actually, that is the real understanding. Anti-aromatic compounds are paramagnetic, means you can see it having unpaired electron through, if will, because it is unstable, so little bit energy also will give, it will generate free radicals, so they are paramagnetic. And since I told that anti-aromatic compounds, if it is containing 7 or more than 7 carbon, so cyclic compound containing more than 7 carbon, such type of anti-aromatic compounds will become non-aromatic. So like here you can see it having total how many carbon? Total 1, here 3 and 4, 5, 6, 7. So 7 or more than 7 carbon will become non-planar. So like here you can see it became non-planar. So from planar it became to non-planar. Sir, how here it is planar? Array, this sp3 degraded its hybridization, it became sp2. So that time it was planar, but since it is highly unstable, so it will break its planarity and at least it will become non-planar. Through that it became non-aromatic. Non-aromatics are more stable than anti-aromatic, so it will move forward, because always you know that reaction or that any species will move from unstable to stable. Next, coming to quasi-aromatic. So quasi-aromatic means when charge is the part of aromaticity. Without that charge you cannot accurate its aromaticity. If charge is the essential part of aromaticity, then it is called quasi-aromatic. So here you can see that carbon oxygen bond will polarize like this. So here positive. So this ring is having 2 pi electron. In that positive is the part of aromaticity. So yes, here also you can see positive is the part of aromaticity. Here you can see positive is not part of aromaticity. Without that also this is aromatic. So this is not quasi-aromatic, it is aromatic. Clear? So once again, stability of this charge containing system we will define by first that sigma resonance in that CPM, cyclopropane methyl cation. Next, after that quasi-aromatic. Then after aromaticity, in aromaticity you know that aromatic is more stable than non-aromatic, non-aromatic is more stable than anti-aromatic. And after that we will define by that all those resonance, hyperconjugation and inductive. So this is the order: quasi, then after aromatic, then after resonance, hyperconjugation and inductive. Before quasi also you can add sigma resonance. Clear? Next, moving further, that as I told that Huckel rule is only valid for monocyclic. More than one cycle if it is coming, then what we have to do? We have to consider its periphery and that maximum conjugation. If overall its result is coming either as a 4n plus 2 pi, then it will be aromatic. If it is coming 4n pi, then it will be anti-aromatic. So like here you can see that this is the periphery, this all those are periphery. Periphery means boundary, and overall that conjugation intersection. So here how many total electrons? 6 pi. So this is aromatic. Similarly, this is the periphery in that double, single, double. So maximum cyclic conjugation, how much? This one. So this is 6 pi electron. Once again, this is the periphery conjugation. In that the maximum cyclic conjugation. So this is the cyclic conjugation. If you will take this one as a like this, so this is not cyclic conjugation. So 6 pi electron. Clear? Similarly here also this is the periphery, and in that maximum cyclic conjugation, this one. It's that intersection is the aromatic. Similarly here you can see periphery. In periphery maximum cyclic conjugation. So you can see this is the maximum cyclic conjugation. Double, single, double, single, double, single, double, single, like that. So this is the periphery also, and its maximum conjugation is also this one. So this bond, if we'll omit this one, so overall this will be one macro only, bigger cycle, one cycle only. In that, how many? 10 pi electrons, so aromatic. Similarly here also periphery and maximum cyclic conjugation. So here 8 pi electron, so it is anti-aromatic. Similarly here you can see periphery, in periphery that maximum total 14 pi electron aromatic. 14 pi electron, yes, aromatic. Here you can see that anthracene. So here that anthracene having, so you know that in anthracene having 4 types of resonating structure. So in that, suppose one resonating structure where in periphery and maximum cyclic conjugation is coming for 12 pi electron. Another also its resonating structure, in that if it is coming 14 pi electron, so that only we will consider. While selecting periphery, select that one which having highest conjugation in periphery. So like here you can see you are missing this one in periphery, this double bond, right? But here all are coming at periphery, means that one is aromatic. Similarly here also all the periphery and maximum cyclic conjugation 14 pi electron aromatic. Similarly this one also. Next, coming to aniline. So in aniline, remember aniline 10. What is the aniline actually? It is di-in system, conjugated di-in, double. So if conjugated double bond system is there, polyenes, they are called anilines. Like here you can see double, single, double, single, double, single, double. So conjugated cyclic polyene systems are called anilines. Aniline 10, remember this one, aniline 10 is non-aromatic, it is exception. But after that aniline 12, it having how many pi electron? 12 pi electron. Means how many pi bond? 6 pi bond. How many carbons? 12 carbons. So this is non-aromatic. Aniline 14, so how many carbon? 14. How many pi bond? 7 pi bonds. So it is aromatic. So here you can see aniline 14, like here this aniline 14, so it having total 7 pi bond. If in between bigger bulky groups are there, so due to that bulky group it will become non-planar. So even though it is aniline 14, due to here presence of bulky group, it will become non-aromatic. But if bulky groups are not there, if it is simple aniline, means here hydrogen will be there, then it will be aromatic. And this is one special entity is azulene. So azulene is also a aromatic compound. This is having 10 pi electron. Next, last, which of the following compounds will give aromatic compounds? Which of following compounds will give aromatic compounds, aromatic product? So here you can see Lewis acid. So it will become AlCl4 minus, and this carbocation quasi-aromatic, 2 pi electron aromatic. Here as sodiums, you know that here this radical it will be generated. So let's suppose here as you are breaking this bond, so here positive charge came and here negative, and this sodium can give 2 electrons, so that 2 electron it is giving to here positive. So overall this became negative, single, double, single, negative. Means this lone pair or this formal charge, negative charge, even though it is sp3, it will degrade its hybridization, means it is delocalized lone pair. So overall 6 pi electron aromatic. Similarly here also this is delocalized overall, so it is anti-aromatic, but since here it is having more than 7 carbon, so it will become non-planar and non-aromatic rather than being anti-aromatic. Clear? Next, predict the dipole moments of the compounds. So predicting dipole moment means we will break bond in such a manner so that what will happen, both side, if aromatic compound is coming, then it will be more stable product. Like here though we cannot do because carbon and oxygen bond is there, so polarization will happen like this only. So as here this is positive single, double means quasi-aromatic, and it is aromatic compound. Yes, bond is favorable, and this is a stable compound due to resonance, and dipole moment will be positive to negative. Clear? So direction of dipole will be like this. Similarly here azulene. So azulene also you have to break in such a manner so that both, if it is getting aromatic, that is well and good, and that only polarization is more stable, means forming more stable product, means that direction of dipole moment is valid. So here you can see as it is getting polarized, so here positive charge and here negative charge, means this one is becoming 6 pi electron aromatic, and this one is also 6 pi electron aromatic. So dipole moment is positive to negative. Similarly here you can, if you break like this bond, then what will happen, this will become anti-aromatic, so will not do like that. If we are doing like this, so here it having also 6 pi electron, here also 6 pi electron, both are aromatic, dipole moment will be positive to negative. Similarly here boron is Lewis acid, so electron is moving like this, so here positive charge came, so overall this also having 6 pi electron, and this one also 6 pi electron. Dipole moment will move this way more effectively because it is forming a stable aromatic system both side, so dipole moment will be this direction. Similarly for this one also. Clear? Next, after this, part 3 is coming, where we will discuss that acidic and basic strength in detail. So that we will discuss in coming lecture, where acidic strength of acid and basic strength of base we will study. Thank you very much.